All right, so looking at this lesson on discrete random variables, let's just get straight to this. We have a game that involves two players rolling a six-sided dice, and the score in the game is such that it's the greater of the two numbers shown. And so, for example, if you roll a 6 and a 5, your score is 6. If you roll a 2 and a 1, your score is 2. And it says if the two numbers are the same, then the score is just whatever's on either die. And so let t be the random variable, the score in the game. So this t we see here is the score in the game. And uppercase T represents the whole set. Lowercase t represents the individual possibilities, getting a score of 1, of 2, a 3, a 4, a 5, or a 6. And so this table, I now want to find the probability. For example, this here means the probability of a score of 1, a probability of a score of 2, probability of a score of 3. And that's what I want to put in here. And so let's find some of these probabilities. So what's the probability of having a score of 1? Well, this little sample space diagram is helpful. First of all, realize there's 36 possible outcomes when you roll two six-sided dice. And to get a score of 1, that'll only occur if you roll a 1 both times. Because if you roll a 2 and a 1, your score will be 2. So there's only one way out of 36 you can have a score of 1. So there's a 1 in 36 probability. To get a score of 2, then you need to roll a 2 on either dice, but 2 has to be the larger number. So it's these three possibilities: a 2 and a 1, a 2 and a 2, or a 1 and a 2. Either way, 2 is the highest number, and so there's 3 possible outcomes out of 36. So 3 and 36. So what about the score of 3? You can have a 3 and a 1, a 3 and a 2, a 3 and a 3, a 2 and a 3, and a 1 and a 3. All of those will lead to a score of 3, which I have there a total of 5 out of 36. And already we can start to see a pattern where it looks like the next one will be 7 out of 36, 9 out of 36, and 11 out of 36. And just to confirm, let's look at the last one to get a score of 6. Any of these here will lead to a score of 6. And there are 11 there. And so these are all correct. And quite often we'll see some sort of pattern forming, but you don't want to jump to a conclusion too quickly. All right, that's the table completed. And this table shows me the probability of different scores in the game. And as well, notice if this is correct, then when you add up all the values, it should always equal 1. And it does. If you add up all these numerators, 1 plus 3 plus 5 plus 7 plus 9 plus 11, you get 36 out of 36. And that's another characteristic of a probability distribution table like this. All the values should always add to 1. So the second part is, what is the expected score in the game? The expected score in the game is the average of all the possibilities. And so in this case, it's, a score of 1 has just a 1 in 36 probability. A score of 2 has a 3 in 36 probability. So if I want to find the expected value, which we can either write with E with a capital T, the expected value of this random variable t, or sometimes we can just use the Greek letter mu, which is also what we use for mean. It is going to be the score for each times the probability for each. So for example, the score of 1 times 1 in 36 probability, plus a score of 2 has a 3 in 36 probability. A score of 3 has a 5 in 36 probability. And I'm just going to go to the end. Lastly, a score of 6 has an 11 in 36 probability. And so the expected value is all of these scores multiplied by the probability of each score added up. It is just the average of all the possible outcomes here. And if you do this, you should get an exact fraction of 161 over 36, or approximately the three significant figures, 4.47. So 4.47, just shy of 4.5, is you could think of it as the average score in this game. All right, for these next two probability distributions, one I give a table, one I give an equation, all I want to figure out is the value of k. So each of these has a variable of k that we need to figure out. And then I also want to find the probability of x being greater than or equal to 1. Well, first let's figure out k. If I look at this table, I can figure out that missing number quite quickly, because whatever this stands for, it doesn't really matter. All these probabilities must add up to equal 1. And so I can quickly see if I add this up, I get 0.75 plus k equals 1, which means k must be Sorry, I didn't add that up properly. If I add these all up, I get 0.8 plus k equals 1, which means k must equal 0.2. It's a weird looking k. Let's make it less x-like. There we go. All right. Let me do something similar for this one before I get to the other part of the question. Here, I have a probability distribution given with an equation in which it's this equation where it's k times e to the power of I, where I can be either 0, 1, 2, or 3. And so that means if I were to imagine a sort of table here, I would have values, possibility of 0, 1, 2, or 3. And the probability of those is k times e to the power of 0. And then this is k times e to the power of 1. This is k times e to the power of 2. This is k times e to the power of 3. But again, we're trying to figure out k. So how can I do this? So all I've done so far is kind of shown that I understand what this equation means. Well, remember again, like before, all of these values, whatever k is, must equal to 1, which means I can solve this equation. How would I solve this equation? I would first take out a factor of k from all of these. So I have e to the power of 0 plus e to the power of 1 plus e to the power of 2 plus e to the power of 3, and all that equals 1. I would divide both sides by all of this good stuff right here, and then I'm done. So to kind of save me writing all this out, I will say everything you see highlighted is approximately 31.1929, and I'm going to divide both sides by that. So k will be 1 divided by approximately this. So I'll make this an approximate. So again, 31.1929 is my approximation of e to the power of 0 up to e to the power of 3. And so that means k is approximately 0.0321 to 3 significant figures. All right, that's finding k for both of these. So now the second part to the question is, what is the probability of x being greater than or equal to 1? Which means, what's the total probability of any of these taking place? And so one way I can figure out that total probability is just add these up. And keep in mind, we know k is 0.2. So one possibility, if I want to find the probability where x is greater than or equal to 1, is just to add 0.15 plus 0.15 plus 0.2 plus 0.25, which leads me to 0.75, which was nice and quick. Another possibility, though, it's also the same as the whole value of the whole sum of 1, take away what we're not looking at, the 0, that 0.25 probability. So quite often this is faster to, instead of actually adding up all these terms, just go the sum must always come to 1 and just subtract what we're not looking at, which in this case is just the 0.25, which notice, of course, is still 0.75. In this case, it's a matter of opinion which was easier or faster, but for the second one, this other idea is going to be much easier. So for this one, if I want to find the probability that x is greater than or equal to 1, I could add up all of these right here, but knowing that k is now approximately 0.0321, or what is significantly easier is just go 1 take away what I'm not looking at, this k times e to the power of 0, which, keep in mind, is approximately, actually put an approximate here, 0.0321 times e to the power of 0. But e to the power of 0 is 1, which means I don't really need that e to the power of 0 here, which means all I really need to do is go 1 minus that k value, which is approximately 0.968. So roughly a 97% probability of that. And before I move on, this idea, when we have to find a probability of a series, a bunch of numbers, quite often it's actually easier to subtract what we're not counting from the total, because they always must add to 1. You can't have more than a 100% probability. So lastly, we have a game where a player pays $2 to roll 2 six-sided dice. If they roll 2 of the same number, for example, 2 3s, they get their money back, so you break even. If they roll 2 6s, they get a jackpot. So what should the jackpot be if this is going to be a fair game? Well, first of all, we need to understand what a fair game means. If something is a fair game, mathematically in statistics, we say that means the expected value is 0. So we need to calculate that. So let's first think about what the probability distribution would be here. And I want to set up. So I'm going to say let C be a random variable, be the random variable representing the cost of the game. Or you could say the prize that you get. Maybe I'll change that. I'm going to be annoying and change this last minute. I'm going to change this to P for prize and the prize value. All right, that said, if I want to make a little table, I have just the possible prizes, and then I have the probability that, oh, that's confusing with a P. Oh, bad me. I shouldn't have P again. Okay, I'll go back to C. I'll leave it as C. Let C be the random variable, the prize. And so in my table, I have the possibilities for the prize, or the cost, whatever you want to look at it, and then the probability of those happening, of big C equaling little c. So what are the possible prizes or costs? Well, there's three possibilities we have to look at. One is which you lose, and it's easy to forget that we could lose. If we lose, your prize is negative $2, or your cost is you lose $2. Because remember, you only get anything back if you roll two of the same values on these two dice. And so most of the times you're going to lose something. And so that means 30 out of 36 times you roll a dice, you're going to lose. And that's because there's only 6 in 36 probability of you rolling the same number. A 1 and a 1, a 2 and a 2, a 3 and a 3, a 4 and a 4, a 5 and a 5, and a 6 and a 6. There's only 6 ways you can do that. And so that means there's 30 ways you can't. So there's a 30 out of 36 probability you're going to lose. And so negative 2 is the random variable cost for when you lose the game. You can also break even. So that's a cost of 0 or a prize of 0. Overall, your net change. And that'll happen when you roll 2 of the 6, but not 2 6s. Because remember, if you roll 2 6s, you win the jackpot. So maybe that there is a 1 in 36 probability, 2 6s. And that's the jackpot. That's what we're trying to figure out. It's called X. And so I don't know what that is. We're trying to figure that out. And now if I go back, this 0 here, in which we break even, it's a 5 in 36 chance. Because they have to be of the same number, but it doesn't include the 6 and 6. So the hardest part is now set up. And so keep in mind, if you're not sure, you could double check and make sure this all adds to 1, and it does. Which means I can now try to find out what this jackpot should be. Because if it's going to be a fair game, the expected value should be 0. So if it's going to be a fair game, mu should be 0, which means the random variable for each. So in case, for example, negative 2, which means you lose your money, which is a 30 in 36 probability, plus breaking even, which I could kind of skip, 0 times a 5 in 36 probability. Clearly that's going to come to 0. Plus what we're trying to figure out, x times a 1 in 36 probability. And keep in mind, if it's a fair game, this always adds to 0. And so now I solve for x. And so pretty quickly, this right here, negative 2 times 30 is 36. That simplifies to negative 5/3. Plus, that's just 0. So then I have plus x over 36 equals 0. If I solve for x, I can say x over 36 equals positive 5 over 3. And pretty quickly, we get to x equals 60. So $60 is the jackpot that would make this game totally fair, which means if the jackpot is exactly $60, over time, no one will come out ahead, neither the players nor the people putting on this game. If the jackpot is more than $60, then over time, the people who are putting on the game will lose money. It's unfair with the advantage going to the player. And if the jackpot is less than $60, it is advantageous to the people putting on this game.